Page tables, data structures for virtual to physical address mapping. In this presentation, we are going to explore page tables, a fundamental concept in operating systems for managing memory. Page tables play a crucial role in translating virtual addresses to physical addresses, enabling efficient and secure memory management. What are page tables? Page tables are data structures used by operating systems to store mappings between virtual addresses and physical addresses in memory management. Consider page tables as address books that the operating system uses to find the actual location, also known as physical location, of data requested by a program. Translates virtual addresses to physical addresses. Page tables are responsible for taking the virtual address, the address seen by the program, and finding the corresponding physical address in the computer's memory. This translation is essential for managing memory efficiently. Enables non-contiguous memory allocation. Page tables also allow the operating system to allocate memory in a flexible way, where memory does not need to be next to each other. Provides memory protection between processes. They ensure that each program stays within its own allocated memory, preventing them from interfering with each other. Basic structure of a page table entry. The contents of a page table can vary, but a basic page table entry will contain the following fields. Valid bit indicates if the page is currently in physical memory. The valid bit is like a switch that indicates if a page is present in physical memory or not. If the valid bit is 1, it means the page is in memory and accessible. If it's 0, it means the page is not in memory. Frame number, physical memory location, also called frame, where the page is stored. The frame number is the address of the physical memory where the page is located. It's like the street address of the data. Protection bits, read, write, execute permissions. Protection bits are flags that control what operations are permitted on a page. Such operations include read, write, and execute. Modified, also called dirty bit, indicates if page has been modified. The modified bit is a flag that is set when the page has been written to. This is important for knowing whether the page needs to be written back to disk when it's being swapped out. Reference bit indicates if page has been accessed. The reference bit is a flag that is set when the page has been accessed. This bit is used to track which pages are actively being used. Address translation process. To convert a virtual address to a physical address. A virtual address is divided into two parts, the page number and the page offset. The page number is used as an index into the page table to find the corresponding frame number. The page offset is the offset within the physical frame where the desired data is located. Address translation formula. Physical address equals page table of P times page size plus D, where P equals page number from virtual address. Page table of P equals frame number from page table. D equals offset from virtual address. Page size equals size of each page, for example, 4 kilobytes. Hierarchical page tables. Hierarchical page tables break down the page table into multiple levels to reduce memory usage, especially for sparse address spaces. Sparse address spaces refer to memory allocation scenarios where a program uses only a small portion of its entire address range. Virtual address is split into multiple parts, each indexing a different level of the page table. In this arrangement, a virtual address is divided into segments that index different levels of the page table. This approach enables a more granular mapping of virtual to physical addresses. Only allocates page tables for address ranges that are actually used. The hierarchical structure allows the system to allocate page tables only for the parts of the address space that are actively in use, conserving memory. Commonly implemented as two-level or multi-level structures. Hierarchical page tables are often implemented with 2 or more levels, creating a tree-like structure that further optimizes memory usage. Trades memory efficiency for additional memory accesses during translation. This design choice means that accessing memory may require multiple lookups across different levels of page tables, which can slightly increase access time compared to a single-level page table. Inverted page tables. Inverted page tables reverse the mapping direction. Instead of indexing by virtual page number, they index by physical frame number, reducing memory overhead. One entry per physical frame instead of one per virtual page. In contrast to traditional page tables, which have entries for every virtual page, inverted page tables maintain only one entry per physical frame. This leads to a significantly smaller table size. Significantly reduces page table size in systems with large virtual address spaces. This reduction is especially beneficial in systems where the virtual address space is much larger than the physical memory. Requires searching like hash table or translation lookaside buffer to find a mapping. To find the mapping for a virtual address, the system needs to search the inverted page table. This search process can be slower than direct indexing and may require additional hardware like hash tables or translation lookaside buffers. Complicates shared memory implementation. The structure of inverted page tables can make it more complex to implement shared memory between processes. Hashed page tables. Hash page tables use a hash function to map virtual page numbers to a hash table of page table entries, reducing memory usage while maintaining fast lookups. Virtual page number is hashed to find the corresponding hash table entry. The virtual page number is processed through a hash function, which generates an index into the hash table. Collision resolution using chaining, such as linked lists of entries. Since different virtual page numbers may hash to the same index, collision resolution techniques are used, such as chaining with linked lists. Combines memory efficiency with reasonable lookup performance. Hashed page tables aim to strike a balance between memory usage and lookup performance, making them suitable for systems where both factors are important. The code block in the slide describes the functionality of hashed page table. Hash value is equal to hash function of virtual page number. Index is equal to hash value modulus table size. Entry is equal to hash table of index. While entry is not null, the following is repeated. If entry.virtualPage is equal to virtual page number, the code returns entry.frame number. Entry is equal to entry.next. The code returns a page fault. Translation Lookaside Buffer, also known as TLB. The Translation Lookaside Buffer is a specialized cache that stores recently used page table entries to speed up virtual to physical address translation. The Translation Lookaside Buffer acts as a cache for page table entries, storing recent translations to reduce the need to access main memory for every address translation. TLB hit rate is 95 to 99%. TLB access time is around 1 cycle. Memory access time is around 100 cycles. Typical Translation Lookaside Buffer size is 64 to 1024 entries. Exploits locality of reference in memory access patterns. The Translation Lookaside Buffer leverages the principle of locality, where recently accessed memory locations are likely to be accessed again soon, improving overall performance. Must be flushed on context switch unless tagged with process ID. During a context switch, the Translation Lookaside Buffer must be flushed to maintain memory isolation between processes, unless it supports tagging entries with process identifiers. Page table structures. Comparison. Let's summarize the different page table structures discussed and compare their characteristics. Simple linear. Memory usage is high. Lookup speed is fast at order 1. Implementation complexity is low. It is best for small address spaces. Hierarchical. Memory usage is low for sparse spaces. Lookup speed is medium because of multiple accesses. Implementation complexity is medium. It is best for large sparse address spaces. Inverted. Memory usage is very low. Lookup speed is slow because search is required. Implementation complexity is high. It is best for systems with limited random access memory, also known as RAM. Hashed. Memory usage is low. Lookup speed is medium because of hash plus possible chain. Implementation complexity is medium. It provides balance between memory and speed. With Translation Lookaside Buffer, memory usage depends on base structure. Lookup speed is very fast for hits. Implementation complexity is medium. It is used in all modern systems. Modern operating systems typically use a combination of these techniques. Hierarchical or hashed page tables with Translation Lookaside Buffer acceleration provide the best balance between memory efficiency and performance for contemporary computing environments. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.